So to that end, let's go back to where we were on Friday. Friday, we left with, we were doing, excuse me. We were doing the molecule drawing on this piece of paper, and we came to OCS. And we recognized at the end of Friday's lecture that the simple structure for OCS with its 20 electrons was far more than what was actually allowed in OCS, only 16. So we knew based on our rule of thumb, we were going to have to add 2 more bonds. The question was, where do we add those 2 bonds? How do we add those 2 bonds? Do we make triple bonds, or do we make a pair of double bonds? And the answer to that question came down to a particular concept. The concept in question was something called formal charge. And if you recall from Friday, formal charge is the number of valence electrons for an individual atom minus its dots minus its bonds. And the key to formal charge is that it needs to be minimized wherever possible. So if I look at these 3 structures, I can see that carbon is pretty common in all of them. Carbon is the same in all of them, in fact. If I look at the formal charge for carbon, I will see that carbon has 4 valence electrons. No dots, and 4 bonds. Regardless of the structure, carbon has 4 bonds. Whether they're 2 double bonds or a single bond and a triple bond, it's still 4 bonds either way. 4 minus 0 is 4. 4 minus 4 is 0. There is no formal charge on any of the carbons in any of the molecules that we drew. Now, oxygen and sulfur are both in the same group. They both have 6 valence electrons. Their formal charge, therefore, is going to be based upon whether they have a single bond, a double bond, or a triple bond. If they have a single bond, 6 valence electrons, charge, 6 dots, and in structure 2, that means that this oxygen has a -1 charge. If they are doubly bonded, like in the 3rd structure, I have 6 valence electrons minus 4 dots minus 2 bonds. 6 minus 4 is 2. 2 minus 2 is 0. Oxygens and sulfurs that are doubly bonded have no formal charge. So in the 3rd structure, we would have no formal charge on the oxygen, no formal charge on the sulfur, and we've already established no formal charge on the carbon. So no charges anywhere in this molecule. For the triple bond, 6 valence electrons, 2 dots, 3 bonds. 6 minus 2 is 4. 4 minus 3 gives me a +1. So the oxygen in the 1st structure has a positive charge. The sulfur in the 2nd structure has a positive charge. So of these three structures, which structure do I have formal charge at a minimum? Which one has the most zeros? It's the third structure, right? This is our correct structure. The double bonded structure is the correct structure here because from a formal charge standpoint, none of the atoms have a formal charge. And since the molecule itself is not charged, none of them should have a formal charge. Now, there are some cases where formal charge is unavoidable. Take your nitric acid, for example. If I follow the same kind of guidelines, I'm going to notice that I have a positive charge on the nitrogen and a negative charge on whichever oxygen is single bonded. That's unavoidable. And the reason why it's unavoidable is nitrogen and oxygen are incapable of breaking the octet rule. So since they can't break the octet rule, they're just going to kind of have to make do with whatever bonds that they can make. Now, this formal charge is stabilized by the resonance. That does help a lot. But nonetheless, there is formal charge there. How do I evaluate these two structures? Well, it ultimately comes down to electronegativity. The structure that is more favorable is going to have the negative charge on the more electronegative atom, which would make this structure with the oxygen having the negative charge more favorable than if it were the opposite. Now, like I said, neither of them are correct. But if this one wasn't an option, we would still choose the bottom structure over this top one because of where the negative charge lies and the ability of that oxygen to stabilize that negative charge with its electronegativity. So any questions about OCS? Okay, so let's go to PF5 then. Now, PF5 presents an interesting problem. I've got 5 valence electrons for the phosphorus, and I've got 7 for each fluorine for a grand total of 40 electrons. Now, if I draw this structure to obey the octet rule, I end up with something like this. I can only make 4 bonds with the phosphorus to fluorines. I'm going to have to kind of make like a bridge to get that 5th fluorine in there. If I fill out all of the dots, I run into another problem. Number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. There are only 38 electrons in this structure. So in order to build off of this structure to get the correct number of electrons, I'm going to have to break the octet rule somewhere. If I follow my guidelines, it would say that I need to have the extra pair of electrons on that center atom. And if I do so from a formal charge standpoint, I have phosphorus, 5 valence electrons, minus 2 dots and 4 bonds. That's a -1 charge. If I look at this fluorine, I have 7 valence electrons, minus 4 dots and 2 bonds, +1 charge. And this is problematic also. It puts a positive charge on a fluorine atom. Now, as we know, fluorine is as electronegative as they come. Fluorine does not do positive charge. Fluorine either does neutral or it does negative. It doesn't do positive. So this structure has some problems of its own right off the bat. But it brings us to an overall point that we need to make. The question is this: when is it okay to break the octet rule? Now, we've kind of brought up the octet rule as this hard and fast scenario where everything's trying to get to 8 electrons all of the time. And the reality of the situation is that that's not always true. Sometimes it's not possible, and other times it's just difficult. So for example, if I have an odd number of electrons, classic examples of this are nitrogen group substances, things like nitrogen monoxide, nitrogen dioxide. In those cases, I'm going to end up with an odd number of electrons. Nitrogen monoxide, for example, 5 electrons from nitrogen, 6 from oxygen, 11 in total. It is literally impossible to get an octet for nitrogen and oxygen with only 11 electrons, because 11's an odd number, 8's an even number. I can't create an even from an odd. Doesn't matter how hard I try. So obviously in those scenarios, you're not going to be able to obey the octet rule. It's literally impossible to do so. There are 2 other scenarios. Hypervalency, going over 8 valence electrons. We've kind of alluded to this, the fact that it's a possibility. We're seeing it in the problem that we're working on right now, PF5. The only way that we can make PF5 is if we break the octet rule somewhere. The question is, when is it okay? And the answer, we have to have an element in the 3rd energy level or greater. So I've got to be starting at sodium and below, because I've got to have access to those empty d orbitals to make it possible. So from the standpoint of the problem that we're working on, fluorine can't break the octet rule. It doesn't possess the orbitals necessary to do so. So phosphorus is the only place that could take on those extra electrons. The 3rd scenario, hypovalency. That is there a scenario where it's okay to have fewer than 8 electrons and not just because it's an odd number? And atoms are capable of doing this, but where we see it the most often is in the boron group. Now, regardless of scenario, the only way that we can break the octet rule in any of these 3 scenarios is if it is backed by formal charge minimization. If by breaking the octet rule, our formal charges suddenly become a lot better, a lot more manageable, we go from -1 to 0, we go from +2 to +1, we see improvement in formal charge, then we know that we're heading in the right direction, that we're doing what we're supposed to do. Classic example of this is BF3 for hypovalency. Boron trifluoride, BF3, to do the octet rule would require a double bond somewhere. I would need to have a double bond between boron and fluorine to do so. Problem is, from a formal charge standpoint, that would give the boron a -1 charge and the fluorine a +1 charge. We just went through why fluorine doesn't do positive. From an electronegativity standpoint, it definitely doesn't do positive. So by breaking the octet rule, by keeping all of those bonds single, boron trifluoride only has 6 electrons around the boron. But from a formal charge standpoint, it has a formal charge of 0. The formal charge stabilizes the otherwise odd scenario with regard to the octet rule. So we come back to our example with PF5. Obviously, this one doesn't work. It gets way complicated quickly. We end up having negative charges and positive charges where we shouldn't. Since we know that breaking the octet rule for phosphorus is okay, why don't we just break it in the simplest way possible? Simplest way possible would be going back to single bonds for fluorine to phosphorus all over the place. If I fill in the dots, and count it up, starting on top left, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. 40 electrons in the structure, matching the 40 electrons that are supposed to be there. From a formal charge standpoint, phosphorus, 5 valence electrons, no dots, 5 bonds, no charge. All of the fluorines are the same. 7 valence electrons, 6 dots, 1 bond. No formal charge there either. So we don't just break the octet rule for the heck of it. There has to be a reason why. And the reason why is apparent here with regard to formal charge. We went from a mess of formal charge, negatives on lower electronegative elements, positives on high electronegative elements, weird bonding structure, to a much simpler design with no formal charges anywhere. That's the whole point. We want to do that whenever possible. And so there are occasions where breaking the octet rule makes a lot of sense. And formal charge is always the driving force for that. Doesn't matter if we're breaking the octet rule by going too high or by going too low. Formal charge is going to be the driving force in either direction. So keep that in mind as you're doing some of those assignments, as you're doing that Lewis structure skill builder for lab, as you're doing your homework and your post-lecture tonight. Those are kind of the central ideas. Let's do one more example before we wrap this part up and do something else. Let's look at this one, I3 minus. Now, the formatting here is a little bit goofy. It should be the triiodide ion, I3 with a -1 charge. We haven't done a charged particle yet. How do we handle that charge? How do we handle that from a drawing standpoint? How do we handle that from a counting standpoint? Well, from a drawing standpoint, it's no different. We're going to treat it just like anything else. From a counting standpoint, I know that I have 7 valence electrons in iodine times 3. The charge, since it's a negative charge, that means we have an extra electron. 1 extra electron turns my 21 electrons into 22 electrons. So 22 electrons in total in my triiodide ion. Drawing this out, again, same kind of process. Iodine in the middle, simple structure, single bonds, fill out my octet. If I do this, I see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons in this structure. I'm supposed to have 22. Now, we haven't dealt with this particular problem before. We've always dealt with the opposite. My structure has too many. I need to start adding extra bonds. When the structure has too few, remember, it's not that we add extra bonds. Adding extra bonds would actually mess up with our formal charge. What we do instead is we add more dots. In particular, we add more dots to the center atom, assuming that the center atom is able to break the octet rule. Iodine is a period 5 element, so yes, definitely can support the extra electrons. Where do those extra electrons go? They go right here in the middle. Where you put them doesn't really matter too much at this point. We're not really interested in shape or structure. We're just interested in making sure that we've got all the electrons in the right place. So now I've got 22 electrons. It matches up. From a formal charge standpoint, the iodine on the left, 7 valence electrons, 6 dots, 1 bond, no formal charge on that left iodine. Iodine on the center, 7 valence electrons, 6 dots, 2 bonds, -1 charge overall. Iodine on the right, 7 valence electrons, 6 dots, 1 bond, no charge on the outside. Okay, so I've got a -1 charge here. Is my formal charge minimized? Or do I need to start playing around with bonding and things? Okay, Aaliyah's made a really good point here. This is a charged particle. This is an ion. There's going to be formal charge somewhere. Remember, the sum of all the formal charges has to equal the charge of the species. So I've got to have a -1 net charge somewhere. It just happens to be on the center atom this time. So this is okay. In fact, this is exactly what we want. If I have a charged particle and the only formal charge is the place where that charge resides, I'm good. I don't need to do any more. If I have a multiple charge, like a -2, I'm going to see two atoms with a -1 charge. Formal charges above -1 or +1 tend to be pretty unstable. So if I have a -2 charge, that means I've got two -1s somewhere. If I've got a +2 charge, I've got two +1s somewhere, or I've got something ionic. Any questions about these Lewis structures? All right. So there are two other topics of utility to us in this chapter. One of them is polarity. The other is bond energy, sometimes referred to as bond enthalpy. Now, in the first, we're going to talk about what it means to be a polar or a nonpolar bond. And the difference is in the sharing of electrons. Now, in covalent bonds, we know that the electrons are shared between the two atoms. And how that looks is basically those electrons in that bond are moving. And sometimes they're associated with the electron cloud of the one atom. Sometimes they're associated with the electron cloud of the other. Sometimes they're both moving around kind of between them. When we have even sharing of those electrons, where the two electrons generally spend equal time around each atom, we call that a nonpolar bond. Nonpolar bonds, truly nonpolar bonds, are relatively rare. Because especially if we have any kind of heteronuclear bond, where we've got different elements on each side, chances are pretty good that there's not going to be an even sharing of those electrons. And when we have uneven sharing, that is the basis of a polar bond. So polar bonds are by far more common. But the ability to form a polar bond, the ability to attract electrons to oneself in that bond, comes down to a property known as electronegativity. Electronegativity can tell us whether we have even sharing and even charge distribution. So in these temperature maps, we are showing the evenness or unevenness of sharing. The hotter the colors are, the more the electrons spend their time in that area. The cooler the colors are, the more time that the electron is away from that area. And so we can see that in a chlorine to chlorine bond, where we've got a homonuclear bond, same element on each side, we can see that the overall temperature map here shows relatively even sharing. Yes, there are some cooler patches on the ends, but again, that kind of makes sense, right? If I've got a bond between two atoms, the majority of the time, the electron is going to be between the two atoms, not off the one side or the other. In a polar bond, like a hydrogen-chlorine bond here, we're going to see that there is an uneven charge distribution. The side that has a hydrogen with the lower electronegativity is cooler than the side with the chlorine that has the higher electronegativity, which has a warmer color. And this is in complete contrast to an ionic bond, where we see that it's not even a sharing of electrons anymore. That electron is flat out gone. The sodium gave it to the chlorine, or the chlorine took it from the sodium, however you want to look at it. The electron is here and not here. Now, up until this point, we've talked about electronegativity in a very qualitative sense. We've looked at it from a standpoint of position on the periodic table, or a general kind of property that we've been calling non-metallic nature or metallic nature. The more non-metallic something is, the more electronegative it is. The closer it is to fluorine, the more electronegative it is. That's how we've been talking about electronegativity so far. But there is a quantitative way of doing it. It's something called the Pauling electronegativity scale. And if we look at an element on the Pauling scale, what we can evaluate is quantitatively how well does that atom attract electrons. The higher the value is, the more it is likely to do that. And so using the Pauling scale, we can establish relationships between two atoms and say, okay, if I've got this atom and this atom coming together to make a bond, what kind of bond is it going to be? Well, if I evaluate its electronegativity on the Pauling scale for fluorine and compare that to the electronegativity for boron, I can see the relationship between them. We use some general characteristics. This delta chi term refers to the difference in the Pauling electronegativities for the two atoms that make up the bond. If the electronegativity difference is 0.4 or below, we tend to think of that bond as nonpolar. Why 0.4? Well, that's the difference between carbon and hydrogen bonds are generally considered to be nonpolar bonds. So that's kind of the upper limit of nonpolar nature. On the flip side, if the electronegativity difference is greater than 2, we don't really consider that bond to be covalent. We consider it to be more of an ionic interaction. The electron's been stripped away from the one atom and given to the other. In that zone in between, we have polar covalent. So we've got covalent bonds with uneven sharing of electrons. The more great the difference is, the more uneven those electrons are shared. One thing I want you to understand about this scale, though, especially in this domain right here, these are all shades of gray differences. The difference between nonpolar and polar, the difference between polar and ionic, they're shades of gray. It's not a stark difference. If I have a 2.1 electronegativity difference, yes, according to this scale, that would be an ionic compound. But if I look at it spectroscopically and I find that there are covalent bonds that exist between them, I shouldn't be too surprised. These are guidelines. These are not hard and fast rules. There is some variability. There is some shades of gray in between the numbers here. So don't take these as absolutes because they're really not. The numbers that we picked here are generally good, but not always completely do we adhere to them completely. This is the Pauling scale. Now, what we see in the Pauling scale is exactly what we were talking about when we thought about them from a qualitative standpoint. As we go down a group for metals, we say that metallic character tends to increase. So the metallic nature of our alkali metals increases, our alkaline earth metals increases, and not surprisingly, their electronegativities go down as they become more and more metallic. On the nonmetal side, we do see a general trend upward as we go up a column, where substances that are more non-metallic, like your nitrogen, oxygen, fluorine, like your halogens, tend to have higher electronegativity values. The last topic that we want to talk about in this chapter are the relationships between bond length, bond strength, and bond energy. Now, if you go back to the beginning of the chapter, we talked about the idea of lattice energy and how lattice energy for ionic compounds is based upon two ideas: charge of the ions, charge generally leading to attraction. The higher the charge is, the greater the attraction. And radius, bond distance. The closer they are, the more attracted they are to each other. The further apart they are, the less attracted to each other they are. Those two same principles show up here in covalent compounds as well. We just call them slightly different things. So instead of charge, because there are no charges in covalent compounds or in covalent bonds, we look instead at bond order. How many electrons are being shared? The more electrons that are being shared, the more attracted the atoms are to each other. After all, a covalent bond is the attraction between the shared electrons and the nucleus of the atoms that are sandwiching them, essentially. The more electrons I put in the middle, the more attractions are going to be present. So a triple bond is going to be more attractive than a double bond. A double bond is going to be more attractive than a single bond. Bond length is handled in a similar way to what we talked about with radius. Bond length, the further apart the atoms are from each other, the easier that bond is going to be to break. The closer they are to each other, the more difficult it's going to be to pull them apart. Well, there's a relationship between all of these. There's a relationship between bond order and bond length. And it kind of is intuitive if you've been following along with the arguments all the way through. If they're more attracted to each other, they're going to be closer to each other. So as my bond order increases, as I go from single to double to triple bonds, I'm going to see my bond go from bigger to smaller to smallest. From a bond energy standpoint, bond energy is the energy that's required to break up a mole of bonds. It's dependent upon a number of things, structure being one of them. But the thing that we can look at also is that the more close our bonds are to each other, the more closely our atoms are to each other, the greater their bond order is, the more difficult it is to break it apart, the more energy it's going to take. Now, all of these can be summarized in a chart just like this one. So this is table 4.7 out of a different textbook. In your textbook, I do believe it is table 4.6. The idea in either case is the same. We can evaluate and compare a couple of different scenarios. So let's look at bond order versus bond length and bond strength. We can see that as we go from single to double to triple bond, two things happen. The bond length decreases as our bond order increases, and our bond energy goes up as we go from one to the next to the next. Okay, no real surprises there. Let's do another comparison. Let's compare sizes. If I'm comparing carbon to fluorine versus carbon to chlorine, the only difference in the atom isn't in the bond order, but in the size of the atom that the carbon is attached to. Fluorine is, according to our atomic trend, smaller than chlorine is. Chlorine has the extra energy level. It's going to be bigger. As a result, we see a bigger bond length and a smaller bond energy. So these three concepts, bond order, bond length, and bond energy, are all intimately tied to one another. And the trend that we talked about tends to hold regardless of what it is that we are examining in this particular domain. Now, one of the applications of this is something called bond enthalpy. And using those bond enthalpies to actually predict reaction enthalpy in a number of different systems. And so in the supplemental video that I'm going to put up on YouTube, I'll walk through these last two slides and how you actually evaluate bond energy to talk about reaction energy from a standpoint of heat transfer. As far as your quiz is concerned, you're not going to see any questions like this on the quiz. You're not going to see any questions like this on the second exam, when we do the second exam in a couple of weeks. The only place where you might see questions like this are in the homework. And so that's what the supplemental video is for. And the final exam, which is produced by the American Chemical Society, might have a couple of questions like this on it as well. That's why it's included in the unit. But as far as things in your immediate purview, you're not going to see a whole lot there. And that's why I have no problem with kind of pushing this onto YouTube and letting you do it on your own time. So Friday, we will be doing chapter 5. We will be starting to look at molecular shape. I'll send you an announcement tomorrow. If you have your lab kit, if it's come in, there's a lab in there that we are not doing, but I kept it in the kit because some of the material that came from it are useful to us. And so I'll tell you what to bring in that regard in an announcement tomorrow that'll help to kind of help us visualize some of the three-dimensional shapes that we're going to talk about in that class. So until then, I'll see you. Have a good afternoon.